We're now going to get on to propagating uncertainties. What is this? It's basically doing maths where you don't just have the numbers, but you have the numbers and the uncertainties. So instead of doing 2 plus 2, you might have 2 plus or minus 0.1 plus 2 plus or minus 0.1. And what's the answer for that? It'll be 4 with an uncertainty. What's that uncertainty? And it's very necessary because very often the number you finally want is not the number you actually measured. So you've got your various measurements with your uncertainties. We've talked about how you work those out, but then you use them in some equation to get the answer. What's the uncertainty in that answer? So for example, let's imagine you want to know the cross-sectional area of a cable, a cylindrical cable, but what you actually measure is the diameter. The diameter has an uncertainty, so the area will be pi r squared, pi over 4d squared, and so you're going to have to work out, if we know the uncertainty in d, what's the uncertainty in pi over 4d squared? So we're going to start off by talking about functions of one uncertain variable, because that's relatively easy, and then later on we'll get on to what happens if you've got 2 or 3 measurements, all uncertain, and you're trying to do maths with them. Now, uncertainty propagation is conceptually fairly simple, but often mathematically rather complicated. So in practice, people will often use computers to do it. There are now very good computer algebra systems that can do maths with uncertainties, just like a calculator. And we'll mostly use them, but you've got to know what you're doing and how it works to begin with. So first of all, let's imagine you've just got one thing you're measuring. We'll call it V, and it's got some uncertainty. And what you want to know is what's the uncertainty in some function of V. R is a function of V. Okay, so how's this going to work? It turns out that calculus is the way to deal with this. So here on this graph we've got V along the bottom and R up the top. And what you can see is, let's say you've measured V as this, but you're going to have some uncertainties. So what that means is V could be anywhere in this range. What that then means is you go up at the two sides here and across to work out what the uncertainty is in R. And down here, because the red line is fairly flat, has a small gradient, a big uncertainty in V actually leads to a small uncertainty in R. But out here, the same uncertainty in V, because the gradient is steeper up here, leads to a much bigger uncertainty in R. So in general, this is assuming that the uncertainties are small compared to the value. This maths breaks down if that's no longer the case. But if that's true, that the uncertainty is small compared to the value, so 100 plus or minus 0.1 is fine, whereas 100 plus or minus 200 is not fine. But if the uncertainty is small compared to the value, then the standard deviation of the result is just the standard deviation of what you measure times dr by dv. Just telling you multiply by the slope of this line, which you can kind of see intuitively off this graph. Now you can just do that, use this equation down here. The other possibility is to use it pre-calculated. People have already worked this out for a bunch of common situations, and you can just use the equation that's already been worked out. So for example, let's say you want to multiply something by a constant. You've got what you'd measure, and you want to know the uncertainty in 5 times what you measure. So constant c is 5. In that case, you do this. You've got r equals cv, differentiate that. dr by dv is just c. So that tells you, according to the equation down here, that the uncertainty in r is just the constant times the uncertainty in v. Very straightforward. So if you're measuring 25 times something, the uncertainty is just going to be 25 times what the uncertainty in the something was. I wish it was all that easy. Raising to a power is a bit more complicated. dr by dv is nv to the n minus 1, and if you rearrange that you find the uncertainty in r divided by r, which is the fractional uncertainty in r, is equal to n times sigma v over v, the fractional uncertainty in v. So what you do is you look at what you're measuring, see what the fractional uncertainty is. So if it's 100 plus or minus 1, that's 1 over 100. Multiply by n, whatever the power is, and that gives you the fractional uncertainty in the result. And you can do similar things for the logs and exponentials, and in fact for sines and coses and anything else you like. And you'll get tables of all these things if you want to use it, or you can just do the calculus yourself